And let's illustrate that, these rules, with a little example. All right, use the properties of logarithms to write the expressions as a single term. And they give us three of them. First off, let's take the natural log of secant theta plus the natural log of cosine theta and express it as a single term. Well, that's a sum of logarithms. That first property, theorem 1.6.1 part 1 said, the log of the product is the sum of the logarithms. So we can take this sum of logarithms and write it as the log of the product of secant and cosine. So property 1 allows us to reduce it down to a single term right there. And arguably this is the answer, but it's a single term, a single logarithm at least. But let's simplify it a little bit and see what happens. There's some subtle nuances here. Let's take that secant theta. That's the same as 1 over cosine theta. So let's write secant theta as 1 over cosine. Now we got 1 over cosine theta times cosine theta. Well, we can reduce that down to 1 and write this as a natural log of 1, provided cosine theta is not 0. And also up here, we had some information that we were taking the natural log of a cosine theta. We can't take logs of negatives. We can't take logs of 0. We can't take logs of negatives. So that thing there, that cosine theta, that better be greater than 0. And by doing this cancellation, we've lost that information. So let's tack it on the side as a condition on this equality. You might be worried about the natural log of secant. Well, secant is 1 over cosine. So if the cosine's positive, then the secant's positive. And we're good to go on both of these two expressions. So I need to add that little extra condition to be mathematically moral about it. And the natural log of 1 is 0. So we've got this simplifies down to 0. I need to put some little more conditions on here though. Cosine of theta is greater than 0. I mean, I get into the weeds too much on this. That puts the following condition on theta. It has to be between, what do we have here? Like an even number minus a half times pi, plus that same even number plus a half times pi. For example, when n is 0, this has to be between negative pi halves and pi halves. Think about the graph of cosine. It's positive on the interval from negative pi halves to pi halves. It's also positive on the interval if I take n equals to 1. This gives us 3 pi halves to 5 pi halves. I'm picking out where that cosine function is positive. You find the solutions, an even numbered one. Maybe the student solutions manual has some solutions to some of the even ones. The odds are they're going to leave this part off. They shouldn't, because it's actually, strictly speaking, it's part of the answer. But we've expressed it as a single term. If you're totally up to date on all of the details, then I really need to add this little part here, because there are theta values for which this thing doesn't equal 0, because this thing isn't even defined. One of them theta values would be what? Pi. I think pi itself, you've got a problem. The next one says, let's take this. This is a little bit easier because it doesn't have that trig stuff in it. Write this as a single expression. Okay, you know how to manipulate logs by theorem 1.6.1. First, let's take this expression. We don't have just a difference because a 2's in the way. Let's get it out of the way. So let's put it on that c as an exponent. 2 natural log c is the same as a natural log of c squared. The power rule, I think they called it, for logarithms, tells us that you can take these coefficients of the log function and put them on the argument inside the log function as an exponent. So that 2 goes inside the log function as a squaring. Now we've got a difference of two things, and we know the log of a quotient is the difference of the logs. This is a difference of logs, so it equals the log of the quotient first divided by second. 8x plus 4 divided by c squared. So that was actually a little bit easier. No caveats on any of this. I mean, c can't be 0. That's implied by what's written over here. So there's that one written as a single term. Let's write the next one as a single term, and starts out kind of similarly. I've got a difference, but the 3's in the way. Okay, we'll take the 3 inside as an exponent of 3. And then we'll have the natural log of, they gave us a cube root of t squared minus 1. Awesome. We'll get the cube root of t squared minus 1 cubed. When we take that 3 from out front and make it an exponent, power rule of log says you can do that. The cube root and the cubing cancel. No need for absolute values. If it was square roots and squaring, I'd think about it for a second. But in this situation, no problems. I don't need any absolute value stuff on these. I do worry about logs and negatives still. And so we get the log of t squared minus 1 minus the natural log of t plus 1. Hey, that's a difference of logs. We can write it as a log of a quotient. Log of t squared minus 1 over t plus 1. Hey, t squared minus 1 factors into t minus 1 times t plus 1. We can cancel those t plus 1s if we're not losing any information. For example, we can't have t equals negative 1, or else we'd be canceling zeros. We'd have division by 0. That was implied from up here because you can't take the natural log of 0. Yeah, well, if you had t equals negative 1 down here, you'd have the natural log of negative 2, and you can't do that either. So this contains the same information that was contained earlier. And though we've canceled, we haven't lost any information like we did in the previous one where I had to do some weirdness with the cosine function. So there's illustrations of these rules for logarithms. Next is the so-called inverse properties of an exponential and a log function. So these are inverses of each other. What one does, the other one undoes. So if I compose these functions, we get the identity function. That is a, the exponential function a with log base a of x as an exponent, make it big enough to see, equals the identity function. So we put the log function inside the exponential function and we just get the identity function. Here we've put the exponential function inside the log function and we get the identity. They interact like squaring and square roots with the caveats introduced earlier. If I square and then take a square root, with the caveats discussed earlier, we'll just get the number back. If I take a square root and then square, we'll just get the number back with the caveats discussed earlier. The caveats being things about one-to-oneness. We made some restrictions on the squaring function when we found its inverse is the square root function earlier. So here, both of these are one-to-one functions, so I don't need any restrictions on domains. I need to be careful. Log function's not defined for non-positive numbers. But we've simply put one function inside the other, and I hesitate to say this. It's like the a and the log base a canceled and left us with the x. It's like the a and the log base a canceled and left us with the x. All right, it's not cancellation, it's composition of a function with its inverse. So it's not cancellation. The effect is the same. The log base a and the a, they're both gone and you're just left with the x. If we were to do this base e, we'd get similar things. E to the natural log of x is x and the natural log of e to the x is x. Exact same stuff. Just a slightly simpler notation of ln of x instead of log base e for the natural log function. Every exponential function is a power of the natural exponential function. A to the x is, well, you can even take this as a definition, in some settings you do, a to the x is e to the x natural log of a. So get that big again for a second. In fact, we might, in a different setting, rigorously define the e to the x function and then say, when I write a to the x, this is what I mean. E to the x times natural log of a. And if you'll think about it, if we take e to the natural log of a, that's going to produce an a and leave us with an a to the x power, if you believe these things we just stated, and they are true. So every exponential function, even those base a, are related to exponential functions base e, or related to natural exponential functions. The book states a change of base formula related to logarithms. It says log base a of x is the same as the natural log of x divided by the natural log of a. In fact, you might even take that as a definition of these other log functions in a different setting. So that means every log function, base a, is directly proportional to, here's a constant of proportionality, 1 over the natural log of a, directly proportional to the natural log function. So every exponential function is related to the natural exponential function. Every log function is related to the natural log function. Your calculator, when you ask it to perform computations concerning exponentiation and logarithms, it actually computes natural logs and natural exponentials, and then it converts them into the base A stuff. You ask for a log base 10 of 1, 2, 3, 4, 5, 6, 7. It finds a log base E of 1, 2, 3, 4, 5, 6, 7, and then it uses this formula to convert it to base 10. The reasons for that I can't elaborate in Calculus 1, but you'll see in Calculus 2 how computations are done using natural logs and natural exponentials, and the preference for natural logs and natural exponentials. That's why they're called natural logs and exponentials. 1.6.54, let's look at another example. Okay, this actually illustrates the inverse properties. They ask us to solve for y in terms of x in this equation. All right, here's your problem. We're trying to solve for y. Y is stuck inside these log functions. How are you going to get it out? Well, probably using an inverse log, which is an exponential. All right, first, let's simplify. I guess this is a simplification. By theorem 1.6.1 part 2, we got the difference of logs. We can write that as a log of a quotient. So we can write the log of y squared minus 1 minus the log of y plus 1 is the log of the quotient, y squared minus 1 divided by y plus 1. Right-hand side, we haven't touched yet, is a natural log of sine x. You could factor this, y squared minus 1 to y minus 1 times y plus 1, difference of two perfect squares. We could cancel the y plus 1s. I'm worried about losing information. I don't lose information in this case. This is similar to one we did above. Let's not get into the weeds too much on that, but this is legitimate to cancel and simplify this down to the natural log of y minus 1. So left-hand side simplifies down to natural log of y minus 1. Right-hand side, we're still stuck with a natural log of sine x. Are you better off than when you started? Yeah, we started out with a y squared term and a y squared, and they were kind of separated. Here, we just have a y term. Now, we still got a problem. That y term is stuck inside that log function. We need to pop it out. How are you going to get it out of the log function? Using an inverse function, of course. What's the inverse of a natural log? A natural exponential. So what we're going to do is exponentiate both sides. So we'll take e to the natural log of y minus 1, this side, equals e to the natural log sine x. Why would you do that? Because I'm trying to get rid of the natural log. And the exponential will compose with that natural log function to give us an identity function. What happens when you exponentiate a natural log? It's like the e and the natural log cancel on both sides, leaving us with y minus 1 on the left and sine x on the right, and we got rid of the log functions. I say it's like cancellation. Technically, it's composition of inverses. You think of it as like cancellation, just don't tell me about it. That's certainly how it behaves. All right, so we end up with y minus 1 equals sine x. By the way, we've lost some information here. We needed y to be greater than 1 because we were taking the natural log of y minus 1. So we get that as an added condition. Sorry, it should be y strictly greater than 1. Y equals 1 gives us a log of 0, and we can't do that either. A little typo there. I'll get it fixed in the notes. Should read y as greater than 1, strictly. We could have also done this by saying, hey, if the log of this equals a log of that, log function's a one-to-one function, and the only way that can happen is when this equals that. So we could have used an argument about the one-to-oneness of a log function. without dragging the exponentials into it. I like dragging the exponentials into it. It's algebraically cleaner to do it that way, in my opinion. So we left off with y minus 1 equals sine x. We're solving for y. Solve for y in terms of x. Put the 1 on the other side, and we get y equals 1 plus sine x, which is probably what the book expresses the answer as, or if you find a solutions manual. But you know, there's a little bit more to it than that. Like I said, we need y greater than 1. So that puts some constraints on the sine function, as with the previous one. Let me not get into this in great depth, but that requires that the sine function be strictly greater than 0, and that puts some constraints on what x can be. I leave it to you to convince yourself that this is correct. But we solve for y in terms of x. We get y equals 1 plus sine x, that not being valid for absolutely all x values, only for these x values here, which it turns out is implied by this. The fact that, hey, if we're taking the natural log of sine x, that sine x thing, it better not be 0 and it better not be negative. This constraint on the x values guarantees that as well. But that illustrates the relationship between logs and exponentials as inverses of each other. Let's do another one. All right. Oh, I like these kind. Let's do one involving radioactive decay. All right. In the last section, we talked about exponential growth. We talked briefly about exponential decay and radioactive decay. We did it in connection with a carbon-14 example. We're going to mention that one again while we're here. The story in this one is the half-life of a radioactive element is the time expected to pass until half of the radioactive nuclei present in a sample decay. The half-life is a constant that does not depend on the number of radioactive nuclei initially present in the sample, but only on the radioactive substance. So, with the amount of radioactive nuclei present at time t given by y equals y sub 0 e to the negative kt, find the half-life. This is the formula we had for exponential decay in the previous section. We didn't do this in the previous section because they're asking us, where do I find something to call attention to? Time. They're asking us to find time, and time is stuck in an exponent. The last example we did, we were looking for something stuck inside of a log function, and we pried it out using the inverse of a log function, an exponential function. Now, we're looking for something stuck inside an exponential function. How are you going to pry it out? Using an inverse function. And the inverse of an exponential function is a log function. So to work this problem, we need logarithms. That's the reason we didn't talk about it in section 1.5. Okay. So the question is, what's the half-life? So the question is, t equals what when the amount present is half of the initial amount? The initial amount was y sub 0. So we want to know what's t when y equals 1/2 y sub 0. You've got an amount of a radioactive element present, it decays away. How long does it take it to decay to half of its starting amount? That allows us to consider the equation y equals y sub 0 over 2. Set that equal to the equation for y sub 0 e to the negative kt. And all we got to do is solve this equation for t. They didn't tell us anything about k. The answer will have k in it. First off, we can cancel the y sub 0s, divide y sub 0 out on both sides. That simplifies then to 1/2 equals e to the negative kt. Cancel the y sub 0s. Now we're trying to get to the t. The question is t equals what? So what are you going to do? How are you going to get the t out of that exponential function? By composing it with its inverse function, the natural log function. So let's take a natural logarithm of both sides of the equation. Natural log of 1/2 equals a natural log of e to the negative kt. What is the natural log of e to the negative kt? Well, remember, it's like the natural log and the exponential cancel. It's composition of inverse functions, but those are gone and you're just left with negative kt. That's why you took a natural log, to get rid of the exponential. So left-hand side has become natural log of a half. Right-hand side has become negative kt. We can solve for t from there. Divide both sides by negative k. We get t equals a natural log of a half divided by negative k. Well, that's the answer. Let's clean it up a little bit because it cleans up. First, let's take a half and write it as 2 to the negative 1. So then we've got the natural log of 2 to the negative 1. And theorem 1.6.1 part, I don't know, the power rule part, I think it was the fourth part, says we can take exponents outside of log functions like that. So this 2 to the negative 1 inside the log function leads us to a negative log 2. Bring the exponent out front of the logarithm as a coefficient, power rule for behavior of logarithms. And now we've got a negative in the numerator and the denominator, so we can cancel those, and this simplifies to the natural log of 2 divided by k. So there's the half-life. Yeah, it's the k was the decay rate, rate constant or something. So of course it's affected by k. If they told us a specific value of k, we could find a specific half-life. And you know what? They did that when we were doing example 4 from the previous section. They told us for carbon-14, K was 1.2 times 10 to the negative 4. So if we plug that 1.2 times 10 to the negative 4 in for K here, we can find the half-life of carbon-14, be the natural log of 2 divided by K, this thing here. Give you that to 4 decimal places. It comes out to a little shy of 6,000 years. 5776 years. So if you pick up something, we had this conversation in the previous section as well. If you pick up an artifact and you measure the amount of carbon-14 present, and it's half what you know it started with, it's half the amount of carbon-14 that's in the environment that this material was interacting with the environment when it was alive. So it has to be something plant-based or animal-based. If it's got half the carbon-14 that it started with, then it must be 5,776 years old. So that's how you can measure the amount of carbon-14, compare it to the initial amount, the y sub 0 amount, and that's known by measuring the amount of carbon-14 in a living environment. You can tell how long it took that original amount of carbon-14 to decay to the amount you measure. If it's half the amount of the original part, it's 1/2 here, then that's how old it is. If it's a quarter, it'd be half of a half, it'd be double this. So it'd be, what's that, 11,500 and some odd, twice this if it was a quarter of the original amount. But if you can measure the amount of the carbon there, you can determine the age. We didn't talk about this in the previous section because it requires logarithms. We could change it from an amount of a half to amount of whatever's observed, and then solve for t using logarithms. And that's how you use carbon-14 and radioactive dating in general to determine ages. It's just an exponential function that has to be solved using an inverse exponential using a log function. Back to the notes. All right, so let's see. Last part of this is on trig functions and inverse trig functions. Already commented in passing, none of the 6 trig functions are one-to-one. So, like when we were dealing with x squared, if we're gonna look for a candidate inverse function, we're gonna have to first restrict the domain of these trig functions to create a new function that is one-to-one. Just like we did in that example with the y equals x squared thing. We erased the left-hand half of that graph and kept x greater than or equal to 0. So we kept the right-hand half of a parabola, and that was a graph of a one-to-one function. It satisfied the horizontal line test. We're going to have to do the same thing with a trig function. So we're going to erase a lot of them, make a new function. When it's going to be like the old function, it's just going to have a different domain. We're going to restrict the domain in such a way that we produce a new function that's one-to-one, and we'll find the inverse of that new function. And just like you had problems taking square roots, you take the square root of 9, you get positive 3 with a square root function. Maybe you wanted the negative 3. Well, a square root function won't give it to you. You're going to have to be conscious of that kind of thing. So when we do inverse sines and inverse cosines, the function, the calculator in practice, will give you one angle out, but it may not be the angle you want. You got to know how to find the angle you want from whatever physical constraints you have based on what the calculator's given you. Standard topic from pre-calculus. So we're going to create a new function that is one-to-one, and this new function then will have an inverse. So we're going to do this by eliminating some of the angles. In all 6 cases, we're going to look for inverses of all 6 trig functions and just draw pictures, really, and not get too involved in details on this. We got other things we got to get to. But we'll always keep the angles between 0 and pi halves. We'll always keep the acute angles, and then we'll include some more angles, and it depends on the trig function as to the additional angles that we'll include to set up a definition of a new function that has an inverse. For example, for the sine function, if we were to take a sine wave would look something like this. It'd wave back and forth along the x-axis. If we took that sine wave and reflected it about the line y equals x, as you do when looking for inverse functions, then we get a thing that waves back and forth along the y-axis, and it violates the vertical line test. Well, what we're going to do is erase a bunch of this sine wave along the y-axis until we get a function. We're going to keep these angles between 0 and pi halves. Can you keep some more? Let's see, between 0 and pi halves, that gives just this piece here. So if we keep that part to satisfy a vertical line test here, we can't include these next bunch of angles, or we'd violate the vertical line test. But we can keep some of these down here. Right? For that matter, we could have kept some of them up here from pi to 3 pi halves if you like. But the standard way of doing it is to keep these angles between 0 and negative pi halves when dealing with a sine function. So we'll keep the angles between negative pi halves and pi halves out in terms of range, and we'll take as the inverse function of the sine function this thing here. So we'll restrict the domain of the sine function, creating a one-to-one function, and then take that function, revolve it about the line y equals x, and that'll produce these inverse functions. That's what the next picture is about. So, and here exactly is a sine function. So we're going to take a sine function that would wave back and forth, centered about the x-axis, and we're going to erase a bunch of it, producing a one-to-one function. So what's graphed here, this bugs me a little bit, is all the information's here, but this is not a graph of y equals sine x. This is a graph of y equals sine x with the restriction that x is between negative pi halves and pi halves. We've erased everything greater than pi halves over here. Yeah, if I draw more of it, we're going to have a violation of the horizontal line test. We won't have a one-to-one function, and it won't have an inverse. Same thing over here. If I add anything beyond there, we're going to violate the horizontal line test again. So we've kept as much as we could. By convention, we keep the piece between negative pi halves and pi halves. You want to keep the piece between pi halves and 3 pi halves, you could make an argument for that. Nobody else does it, so don't do that. There's nothing math wrong with it. It's just not the standard way of doing it. Keep this segment here. That's a one-to-one function. That has an inverse. And we can talk about the domain and range of the inverse. Actually, if you'll take this little thing here, rotate it about the line y equals x, it will produce what we were just looking at. It'll produce this thing here. So that's the idea for the cosine function. Let's do the same thing. We'll keep the angles between 0 and pi halves, meaning we can't keep any of these angles over here, or we'd violate one-to-oneness. And we'll keep the angles between pi halves and pi. It gives a continuous thing that includes the acute angles, 0 to pi halves, and that's kind of the standard. Includes the angles between 0 and pi halves and try to make the thing continuous. So for cosine, we'll keep this part of the wave. Tangent function, remember the wave of a tangent function looks like this. There's another one over here and another one over here, and they're off to the left as well. Well, let's keep just one of them. And that will give us all of the behavior of the tangent function. I can't include more than that or I violate one-to-oneness. And it looks like it's negative pi halves to pi halves for the tangent function that we'll keep. Cotangent function, we looked at this recently. has a graph that looks like this. This is one wave. There's another wave over here and other waves to the left. 0 to pi, we'll keep that part of the cotangent function. This is not the graph of a cotangent function. This is a graph of the cotangent function where x is restricted to be between 0 and pi. I kind of wish they'd tack that on up here, but that's what we're dealing with. Like I said, the information is contained here. And then the secant and the cosecant, those are discontinuous and a little more odd. We'll definitely keep the parts of those secant functions between 0 and pi halves and some more stuff. Our book says we're going to keep the angles between pi halves and pi as well for secant, with some constraints about where these vertical asymptotes are. For cosecant, we'll keep negative pi halves to pi halves. Got to throw 0 out of that one because of some division by 0. But we're making these restrictions, and each of these blue graphs here, those are all 1-to-1. Those are not, as they're labeled, that's not the graph of sine, cosine, tangent, cotangent, secant, and cosecant. That's the graph of new functions that equal sine, cosine, tangent, and so forth, respectively, but only on some subset of the domain of the original function. Yeah, we've restricted the domain, creating a new function that's 1-to-1. These things here, they're 1-to-1, they got inverses then, and that's what the inverse functions are. So what we'll do is take each of these 6, we'll revolve them about the line y equals x, and use that for the inverse function. We've already seen what sine would look like. I'll go to the next page. Here's the sine function that we had. The inverse cosine function will look like this. The inverse tangent function will look like this. I mean, that one's probably the easiest one in your mind to visually rotate about the line y equals x. And here's the rest. So here's what we get for the inverse trig functions. There's a couple of notations, and when preparing these notes, I see the folks that wrote the book, they can't really make their mind up on what notation is best as well. The inverse sine function sometimes is written as y equals arc sine of x. Sometimes it's written sine inverse of x. That little -1 there, meaning inverse trig function, not meaning reciprocal. It's a standard notation. You need to get used to it. When you see that little -1 on a function, it means the inverse function. It doesn't mean the reciprocal. You see that little -1 on a number, it means reciprocal. But on a function, it means the inverse function. And I can see this latest version of the book, they've used the arc notation, arc sine instead of sine inverse, arc cosine, arc tangent. Some calculators will have an ARC button for the arc function. Some calculators will have an INV button for the inverse function. And it'll include inverse trig functions and maybe inverse log and exponentials even. But standard notation is to use these little -1s like we have here or here to indicate inverse functions. You need to get used to that. It doesn't mean exponent. The book has gone to the trouble to refer to arc sine and arc cosine instead of sine inverse and cosine inverse. Yeah, I feel their pain. They're trying to avoid confusion with inverse, with reciprocals, with these -1s. This is not an exponent, it's something else. It means inverse function. So that's the reason they're sticking with this arc stuff. But the rest of the world ain't gonna coddle you that much. And you need to be adaptable enough to recognize that as an inverse sine function and an inverse cosine function. Here's some specific definitions we would get out of these. It's a matter of what are the domains and ranges that we get from these inverse trig functions. Let's do an example, example 72. So I haven't skipped anything, have I? Have not. And with that, let's concentrate on, it deals with inverse cosine. Let's look at this one. So what happens when you're dealing with a cosine inverse or an arc cosine function? The kinds of angles you get out of an inverse cosine function are angles between 0 and pi. Angles between 0 and pi. I need to know the range of these functions. if we're actually going to go through and find some inverse cosines. If it were inverse sine, it's a different range. It's negative pi halves to pi halves, and we went through all the pictures to explain why they would do it like that. So with this in mind, the range of the cosine inverse function is 0 to pi. Let's do one last example that has us finding some cosine inverse values. All right, and I copied these straight out of the book as well. So somewhere in there, the book's given up always using this arc notation. They've actually used the inverse notation here. They want to know the cosine inverse of a half, the cosine inverse of negative 1 over the square root of 2, and the cosine inverse of the square root of 3 over 2. All right, part A and part C, I know these are special angles. We made a whole table of special angles in the section on trig functions. Was it a couple of sections ago, I guess, when we did the trig section of chapter 1. So if we say theta is a cosine inverse of 1/2, that means two things. It means the cosine of theta is a half, cosine of theta is a half, and remember the range of the inverse cosine function was 0 to pi. So it means cosine theta is a half and theta is between 0 and pi. Well, I'm going to use our knowledge of special angles, and I refer you to section 1.3, it must have been when we did trig functions. Section 1.3, there was a particular figure where we looked at special triangles, 30, 60, 90 triangles, 45, 45, 90 triangles, if I use the degree names for them, which is common. Then from those triangles and just our knowledge of special angles, pi thirds has a cosine of a half, and pi thirds is between 0 and pi. Any other angles between 0 and pi that have a cosine of pi thirds? No. If there was, we wouldn't be dealing with a one-to-one function, and we've restricted the cosine function until it's one-to-one. And this thing here is the inverse of that one-to-one function. So I guarantee you there's only one angle between 0 and pi that has a cosine of a half. And we know the cosine of pi thirds is a half. Similarly, if part C, I'm jumping to part C here, we'll give more of an explanation on part B. This is pretty cheap here. I'm just appealing to knowledge of special angles. If theta is the cosine inverse of square root of 3 over 2, then the cosine of theta equals square root of 3 over 2, and theta is between 0 and pi. You know a special angle that has a cosine of square root of 3 over 2? I know you do if you had time to think about it. It's pi 6. The cosine of pi 6 is square root of 3 over 2, and pi 6 is between 0 and pi. They give us just little positive numbers in there, then we're good to go. We'll use acute angles, and it'd have to be special angles or we couldn't answer these things. Pi 6 works. Any other angles in there? No, we fixed that. There's only one angle between 0 and pi whose cosine is square root of 3 over 2, and we know from our knowledge of special angles that it's pi 6. Okay, let's look at part B, where they give us a number that you might recognize, negative 1 over the square root of 2, or square root of 2 over 2 if you rationalize the denominator, but it's negative. So that one's slightly more interesting. So for part B, if we set theta equal to the cosine inverse of negative 1 over the square root of 2, negative 1 over the square root of 2 is the same as negative square root of 2 over 2. Maybe that number sounds more familiar to you. I don't care. They both represent the same number. Here we've got an irrational denominator, and here we don't. I'm just not at all hung up on that. But if theta is a cosine inverse of negative 1 over the square root of 2, or square root of 2 over 2, then we need the cosine of theta to be negative 1 over the square root of 2, and we need theta to be between 0 and pi. Cosine of theta, if it's negative 1 over the square root of 2, that's negative. So this angle can't be between 0 and pi halves. Between 0 and pi halves for acute angles, sines, cosines, tangents, everything is positive or non-negative for first quadrant angles. So it can't be a first quadrant angle. If it's between 0 and pi and its cosine is negative, it actually must be between pi halves and pi. Between pi halves and pi, it must be a quadrant 2 angle. Its terminal side must lie in the second quadrant. Well then, let's use reference angles. A topic our book mentions in passing. It doesn't go into great depth. What I want to do is basically I want to find a point on the unit circle where the y coordinate is this thing here, -1 over the square root of 2. So we'll get a y coordinate of -1 over the square root of 2. That occurs, if you like, negative square root of 2 over 2. When we have a reference angle of pi force, we had a special triangle, 45, 45, 90 triangle that we looked at in section 1.3. We did problems similar to this in 1.3. We've got a 45, 45, 90 triangle I could stick in right here. The length of this side would be square root of 2 over 2. The length of that side would be square root of 2 over 2. The coordinates of this point would be square root of 2 over 2, square root of 2 over 2, except second quadrant, the x coordinate would be negative, the y coordinate would be positive. That's second quadrant behavior. That reference angle would be pi force. So this is what the reference angle is. It's the angle between the terminal side and the nearest piece of the x-axis. Well, if that's pi force, that gives this point here, then the angle measured in standard position must be 3 pi force. I want an angle between 0 and pi that has this as its terminal side. 3 pi force must be the angle. Theta equals 3 pi force. Can you find another angle that has a cosine of this part here? Can you find another angle that has a cosine of -1 over the square root of 2? Yeah, how about this one that goes around once and then goes an additional distance of 3 pi force? That'd be 2 pi plus 3 pi force. That also has this cosine. Yeah, but it's not in the interval 0 to pi. It's too big. I could have gone in the negative direction. Here's an angle. It's -5 pi force. We start at this initial side and go in the negative direction. That's also an angle that has a cosine of negative square root of 2 over 2. Yeah, but -5 pi force is not in the interval from 0 to pi. So inverse trig functions give you specific angles. It's going to give you an angle, in this case, between 0 and pi. Cosine inverse gives you an angle between 0 and pi. You may be working a physics problem, and you don't want an angle between 0 and pi. Well, a cosine inverse function's got no pity on you. It's giving you an angle between 0 and pi. Maybe you wanted that angle that was -5 pi force. So, well, then you're probably going to have to draw a picture and know how to interpret what the inverse trig function gives you in terms of what you know. And what you need may be driven by some sort of physical problem, an engineering problem, a physics problem. And the inverse trig function is not going to cooperate just ideally. That's what you get with inverse trig functions. You're going to have to know how to interpret things and how to change what the calculator may give you into the angle you actually need. So a little warning on inverse trig functions, inverse functions in general, that's a concern. But that takes care of, excellent, that takes care of chapter 1 and all our preliminary material. So we'll start chapter 2 next, and we'll start the real calculus thing next, and we'll start talking about limits. We'll try to cover in calculus 1, chapters 2, 3, 4, and 5. We've got 4 chapters of stuff to go on the calculus material. Have a nice day. I'll see you in chapter 2, section 1 soon.